Hey everybody, welcome to IEC Indy's second year, first semester final exam review. You will be required for credit for tonight's class to watch this video in its entirety, to take a quiz based off the video and whatever else I assign for today's class, plus the hands-on lab that you will be expected to be in class for during your allotted times. If you don't remember what your allotted time is, look on the CMS. It is the first thing you'll find. So look on CMS to find your allotted time when you are required to be in class on Monday, December 7th. Just a few things before we get into the review. Just a few things here before we start into the review. There may be more on your exam than all that we cover here in this video. As you study for your exam, please take the time to review your notes from class as well as previous recordings, especially if you have certain difficulties in a subject or two. Those recordings should be up on the big blue button, and you should be able to access those at any time just by going back to the same big blue button link for that lesson. When we do come to take our test, you will only be allowed to use your handwritten notes, your code book, a calculator, as well as any of the handouts that I've passed out to you, such as your load calculations, your RLC circuits, and all those formulas, and your box fill chart in order to fill out box fill calculations. Be sure to fill out the video quiz at the end of this video. In order to receive attendance for tonight's video, you will have to log into the big blue button, comment in the comments that you are here, and take the video quiz. As well as there will be a code quiz required for tonight's class. It'll be code quiz 217. You will be required to fill out both quizzes. Now, I will leave the code quiz up an extra day since you're going back and forth to our hands-on lab, but it will be closed by the end of the day, the next day. So do not delay in filling out that code quiz. It's not a hard code quiz, and actually it will be very helpful for you on your final exam. Let's jump right into our review for first semester. Lesson 201 is where we started, so let's start right there. Lesson 201, definitions, working spaces, and branch circuits, hazardous locations, voltage systems. Now, some of the things that we're going to talk about, or not necessarily talk about, but some of the things that you will be questioned on your final exam is a lot of basic code. You're going to need to know how to navigate your code book. I'm going to be asking you questions of everything from 90.1 all the way to probably into the 500s for your hazardous locations. So know how to navigate your code book. Looking at Article 100, that's where you're going to find your definitions. 90, Article 90 is where you get the general scope and the purpose and the arrangement of the code. What is the purpose of the code book? Well, it's for the practical safeguarding of people and property. 90.1. That's the very beginning of the code book. The whole purpose of the code book is for the protection of people and property. Like I said, definitions you'll find in Article 100. Know how to navigate through that. Know how to be able to identify what's accessible, what's a non-coincidental load, what's a continuous load, and etc. So that's all in Article 100. Article 110, you're going to find a lot of your clearance spaces in Article 110, especially 110.26. So recall the requirements for electrical installations of equipment and conductors according to Article 110. Again, know how to navigate your code book. Take the time, look up the keywords in the index, look at the table of contents, compare the two, and find your answers. Just like we have all year, just like you did last year. So I know the code updated, navigation hasn't changed. Also recognize your voltages and your properties of various electrical systems. That means I want you to be able to identify what the multiple systems that we typically come in contact with as commercial or residential electricians. Also recall the branch circuits requirements for 210 GFCI. We'll get back to that. But if you look at this right here, this is a voltage summary roughly of what voltage systems that most commercial and or residential electricians typically deal with. Now you get into higher stuff when you get into more industrial electrical work, but for now we're just talking a bit strictly about these four systems. You got your 12240 volt single phase 3-wire system. That's your residential system. That's what you find in most houses. As opposed to the 3-phase systems like the 12208 3-phase 4-wire system or the 12240 3-phase 4-wire system. The 12208 3-phase 4-wire system has 120 volts to ground and 208 volts line to line, whereas the 12240 volt system up there in the top right corner of your screen, you have 3 different voltages available. You have 120 volts to ground on the A phase, 208 volts to ground on the B phase, and then again 120 volts to ground on the C phase. But if you were to go phase to phase or line to line, you would actually get 240 volts between A and B, between A and C, or between B and C. And there it spells out for you what the different breaker types will actually allow you to utilize coming off of your breaker panel. So this is in the back of your manual. Please look that up, get familiar with that. You will not be able to use this in the quiz, but if you put this in your handwritten notes, there you go. And like I said, we will get into have questions about hazardous locations as well. So they'll be sprinkled throughout the test. Please know how to navigate the different hazardous locations like you've been doing all year through your homework. You'll find everything from class 1, 2, and 3 locations to motor fuel garages. I believe there might be an aircraft hangar question in there too. Maybe some healthcare. So know your hazardous locations. 202, service calculations. Yeah, we're going to have some service calculation questions in the final. I will not be asking you to completely calculate an entire house. That will be coming soon next semester. But as for now, for your midterm, you're just only going to be required to know the code references. This is why I say you can use that worksheet, that handout that I've given you on single family and multifamily dwelling unit calculations. Know your codes. Like in Article 210. In Article 210, dot 11, it gives you your required branch circuits, like your small appliances, your laundry, your bathrooms, and etc. Whereas 210.52 gives you your required placement of outlets. You get all the way into 220, it gives you your required allowances in kVA for each of those circuits when sizing the house. So know your code references, use that worksheet. Remember that, like I said, in 220.52, small appliance circuits, each of those are rated up to 1500 VA per circuit. Same with your laundry circuit, 1500 VA. General lighting load. Know the tables for derating in general lighting load. Table 220.42, along with your square footage, found in 220.14J. 220.14J says that a general lighting load in a dwelling unit, you're going to take the square footage of the house, and what are you going to multiply that by? You're going to multiply that by 3 VA. So that's 3 volt amps per every square foot for the entire square footage of the house. And that square footage is of the habitable living space. That doesn't include open porches. That does not include garages or unfinished rooms, unfinished basements, attics. It's the habitable spaces per floor. So when you're calculating your square footage, you take your total square footage for the entire structure of habitable living space and you multiply that by 3 volt amps per square foot. Therefore, let's say you have a 1,500 square foot home. You multiply that by 3 volt amps, you're going to come out with 4,500 volt amps for that square footage. Then you add your small appliance circuits to it, you add your laundry circuits to it. Once it's all added together, then you can use table 220.42 to calculate the demand required on that general lighting load. So know those things. Write it down, put it in your notes, go back and dig out your notes from class. You will be asked some questions based on that. What code article tells me I need to calculate dryers at 5,000 volt amps as opposed to their nameplate if it's lower? What if the nameplate's higher? Do I calculate it at the nameplate or do I stick with 5,000 volt amps? Know the code references. I believe that one is 220.54. And then also know your code references for multifamily and for your optional load calcs. There won't be a whole lot of those, but there will be a couple sprinkled throughout the exam. 203, we're getting into services now. Services, know your service definitions, the fundamental understanding of the clearances as well. But your key components for your electrical services: what's your service point? What's your service lateral? What's your service drop? What's your service underground service conductors? What's your service equipment? All this is found in Article 100 as well as in Article 230. We went over this in great detail in class. Make sure that you have it in your notes what those details are. Especially when we get into the fundamental understanding of clearances. Clearances with services is a big deal. Not only the clearances above, but also the cover for underground services as well. Cover for underground services, I believe, is found in table 300.5. So 300.5 will tell you where to find your coverage for underground installations. For your overhead service equipment, you're going to find that in Article 230. I believe it's going to be 230.24. We'll get to that in a second. Here's a drawing, just again to picture some of the terminology of a service. You have an overhead service here, obviously. They're saying that the service point is at the weatherhead. Now, the service point is where the utility stops and the commercial or the customer begins when it comes to responsibility. After the service point, any work that needs to be done on the premises wiring or on the service entrance is done by the electrician. Before the service point, where you see the service drop over there in the top left corner, that's where the utility owns the conductors, and they would have the responsibility for those conductors. And you see there you got your point of attachment, service entrance conductors, type SE cable in this scenario, then your meter socket, then you have your service equipment, which is your panel board with your main breaker. Now, newer codes actually are requiring there to be a disconnect outside, which is where the main breaker will be. But that's that's 2020 code changes. So, other things to keep in mind: clearances from windows. It's a 3-foot minimum clearance from windows that open. Means that if you are running service conductors outside and you have to span across the side of a building, you cannot come within 3 feet of a window that opens or a door frame, any kind of barn door, you name it. You cannot span that wire any closer than 3 feet. Now, if it's a fixed window, it doesn't open, it technically doesn't matter. Not necessarily great practice, but it technically doesn't require that 3-foot minimum. But if it's an openable window, 3 foot minimum, no closer. And then clearance from ground, yes, it was Article 230.24b. So know your clearance from grounds for those scenarios here. You have 10 feet for subject to pedestrian traffic only, and it's 150 volts or less. 15 feet if it's not subject to truck traffic and over 300 volts to ground. And then trucks over tracks of rail or railroad tracks, 24.5 feet. You need that extra clearance to clear the double stacked train cars. So yeah, clearance from final grade, that's what we're talking about. 10 feet, 12 feet, 15 feet, 18 feet, and 24.5 feet. All that is found in Article 230.24b, and it's 1 through 5. And again, more Class 2 installations. Those are going to be found in Article 502. Remember your classified locations. Class 1, Class 2, and Class 3. And what they're what's the word I'm looking for? Those what they represent, what defines that location. Like Article 500 is a great place to start when it comes to classified locations. And now Class 1, Division 1, you're dealing with ignitable gases or vapors. Class 2 is you're dealing with a location under the normal operations would be dealing with ignitable dust. And then Class 3 would be dealing with ignitable fibers under normal operating conditions. So those are classified locations dealing with vapors, dust, and fibers. All things which can create explosions. So know how to navigate those code references. We've been doing it all year through your 500 homework. There will be some classified location questions throughout your quiz or your final. Lesson 204, Conductor and Overcurrent Protection, Class 3 installations. What I'm really looking for out of Lesson 204 is knowing your characteristics and the installation practices of your conductors. Know your fundamental understanding of ampacity, ratings, and ambient temperature of circuit conductors, and master the purpose of and selection of fuses and circuit breakers for the protection of conductors and equipment. Now, if you look back at 204.1, I've given you a table there, table 310.4. That's for understanding the different types of insulations, knowing what they're rated for. Is it rated for a wet location? Is it rated for just dry location only? Is it rated up to 300 volts? Is it rated up to 600 volts? All that information is found in table 310.4. Now 310.16, 310.15b1, and 310.15c1 are 3 tables that you will utilize for ampacity corrections in conductors based on the insulation. Your insulation tells you what the conductor is rated for, whether it's rated, if it's a 60-degree wire Celsius, if it's a 75-degree, or if it's a 90-degree wire. THHN, for example, is a 90-degree wire. So all of our correction factors, when we are correcting for more than 3 current carrying conductors in a raceway, or temperature changes, are going to be done out of the column that that insulation belongs to. So if it's 90-degree insulation, I'm doing all my correction factors in the 90-degree columns of all 3 of those tables. So table 310.16, I find my ampacity, my starting ampacity for that conductor. Table 310.15b1 gives you the table is written in decimals, but it's the percentage of the starting ampacity that is usable in a certain temperature. And then 310.15C1 is a percentage as well of the starting ampacity or the overall ampacity allowable in a raceway with more than 3 current carrying conductors. And that's all dependent upon if you have 4 conductors, if you have 9 conductors, if you have 10 conductors. The higher the amount of conductors go, the less ampacity that conductor is able to carry. Because remember, they're contained in a raceway together. Each of them are generating heat, and that heat's going to affect the conductors that share the raceway. And as that heat builds up, the resistance builds up, amperage builds up, which creates more heat, and then the insulation breaks down over time. So that's the whole purpose behind this. So if we have to increase the size of our wire to lower its resistance to overcome those heat factors, that's what we need these tables for in order to determine what size wire we should really be running in this raceway, as opposed to just pulling 12 and calling it good for a simple branch circuit. It may not always work. And then 240.6a, master the purpose and selection of fuses and circuit breakers for the protection of conductors and equipment. Your standard size circuit breakers and your standard size fuses are going to be found in table 240.6a. So when you have been given permission to size up to the next size breaker, you're going to find that next size breaker in table 240.6a. I'd write that one down. That one might come in handy. Table 240.6a. And we're going to also talk about branch circuits, feeders, and taps. I really don't have a whole lot of taps questions on this exam, but there may be a branch circuit or a feeder question. So know your definition. What's the definition of a branch circuit? Well, a branch circuit is defined as the conductors after the last overcurrent protection device. And feeders would be everything between the service entrance conductors and the branch circuits. So if it's after a breaker, or if it's after a fuse and it's the last fuse or breaker in line, then it's a branch circuit. If it's in between that last overcurrent protection device and the service entrance, then it's a feeder. That's very generally speaking, but know your definitions. They're found there in Article 100, as well as Article 210, as well as Article 300 and 240. (205) Grounding and bonding. 205, 206. Know your terminology. Know your terminology for grounding. The purpose of grounding. The primary purpose of grounding metal equipment and enclosures and raceways to the grounding electrode system is to keep all the parts at the same voltage and to limit voltage surges. It means you're protecting everything in case there's lightning strikes. If there's a power surge coming from utility, all of this is to prevent line surges. You're doing that by creating a low impedance path to ground. Now that low impedance path to ground, what I'm talking about here is it's more of there's a low opposition to current flow. Just like if it was a low resistance path. But overall impedance, which we've talked about when dealing with RLC circuits, impedance is just the total opposition to current flow. Our grounding system should have a low opposition to current flow. And this is to keep the breakers from, this is to ensure that the breakers trip when the fuses pop when an overcurrent does take place. More grounding terminology for you. Grounding electrode system. Grounding electrode is a conducting object through which a direct connection to earth is established, like your ground rod, your building steel, metal water pipe, you name it. They're all listed there in 250.52 is your code reference for grounding electrodes. Table 250.66, you can kind of see it with my camera right there, but table 250.66 is where you size your grounding electrode conductors that connect to your grounding electrode system. So if you have a grounding electrode, which about most of the services you deal with have, your grounding electrode conductor would be sized based off of table 250.66, and I believe that that is sized solely on the size of the ungrounded conductors, not necessarily what the breaker is, but it's sized on the ungrounded conductor sizes. So let's look in here real quick. 250.66. Yes. So like I said, if you have a service that utilizes 1/0 copper, at that point you're required, according to table 250.66, to run a 6-gauge grounding electrode conductor to the grounding electrode for that system. So table 250.66 is where you size your grounding electrode conductor, or your GEC. Your bonding jumpers, your main bonding jumper is going to be sized off of table 250.102C1. Now that's the supply side equipment bonding jumper. That's going to be on the main. That's not necessarily your load side connecting your equipment grounding conductors to each other. This is the line side, or the supply side. That's table 250.102C1. It's very similar to table 250.66, but that is for your bonding jumpers. And then your load side would be sized off of table 250.122. That's the same table for your equipment grounding conductor. And that's going to be based off of the overcurrent protection device protecting those conductors. So, grounding electrode conductor, 250.66. Main bonding jumper, 250.102C1. Load side bonding jumpers, equipment bonding jumpers, 250.122. (207) Ohm's Law. There will be some Ohm's Law questions in the final. Be familiar with your Ohm's Law wheel. Be familiar with the Ohm's Law formulas and how to break down true resistance of something. Fixed resistance is a better way of putting it, versus the applied voltage and the applied amperage due to the applied voltage. What is your constant? Know how to figure out, using your constant, what your amperage would be, what your power would be when you apply something to that, when you apply a certain voltage to that constant. Like in this situation here, Ohm's Law formulas that you would want to memorize right off the get-go is I equals E divided by R. That's current equals voltage divided by resistance. Resistance is the one constant in almost every Ohm's Law work problem. Resistance is fixed. Doesn't matter if I apply a lower voltage to it or a higher voltage to it. That resistance is the same, give or take a little bit with heat. But if I apply a certain voltage to that resistance, it won't give me the same amperage if I apply a higher voltage than a lower one. My amperage will go up with lower voltage. My amperage will come down with higher voltage. The greater the amperage, the greater the voltage, the lesser the amperage, and etc. So I'd write these formulas down in your notes. I equals E divided by R, E equals I times R, and R equals E divided by I, as well as these guys right here. P equals I squared divided by R. That's a one that I use a lot. P equals I squared divided by R, as well as R equals E squared divided by P, depending on what I'm working with. If I've been given just the power, or if I've been given just the resistance when I'm dealing with a certain applied voltage. But I'd write these formulas down, put them in your notes. They will come in handy. You'll be using them not just for Ohm's Law questions, but other Ohm's law questions you don't realize are Ohm's law, like transformers, RLC circuits, you name it. I'll leave this. You can pause the video here and write these formulas down and put them in your notes. 208, conduit fill, box fill, pull box sizing, raceway and cable support. Guys, what I'm getting at here is you need to know your code references for your different wiring methods. Article 334 is for NM cable. Article 350, I think it's 358 for EMT. I'd have to look it up. I don't have it memorized. But know how to navigate the code book when it comes to what wiring method is found in which code article. Know your dots. Dot 10, uses permitted. Dot 12, uses not permitted. Dot 30, you're supporting and you're securing, etc. Chapter 9, we're getting into conduit fill now. Conduit fill. In Chapter 9, it gives us 3 tables that we base our conduit fill out of. Chapter 9, Table 1, Table 4, and Table 5. Table 1 gives us a percent of cross-section of conduit and tubing for conductors and cables. If I have one conductor, I believe it's 53% that I'm allowed to fill in that raceway of its total cross-section. So if I were to take that conduit, cut it in half, and be able to see it just like an open pipe, that cross-section, that center of the conduit, I'm only allowed to fill up to a certain point before I've overloaded that conduit with conductors. So the percentage that I'm allowed to use is found in Table 1. I believe one conductor is 53%, 2 conductors I think was 35%, and three or more was 40%, which is what is the most common if you really think about it, is 3 or more. After that, the Table 4, the NEC gives us Table 4 to give us dimensions and percent of area in conduit and tubing. So we don't have to sit here and measure every cut section of conduit. Gee, I wonder if I could fit 12 gauge wires in this 1/2-inch pipe. Well, probably not. But you don't even have to measure that to figure it out. Plus, you could always just use common sense, but that doesn't exist all the time anymore either. But so they give us table number 4 here that lists for us the dimensions of each trade size conduit or tubing, and then it tells us the percentage fill for what our application may be. It gives us the 40% if we have 3 or more conductors. It gives us the 53% if it's just one conductor. It gives us the 35% if it's just 2 conductors. What if it's shorter than 24 inches? That would make it a conduit nipple, and we can fill that up to 60%. Table 4 gives us all of those percentages, so that makes our math a lot easier. And so to break it back down, Table 1 tells us what the standard is. Table 4 applies the standard to each individual conduit or raceway. And then Table 5 gives us the actual dimensions of the insulated conductors, so we know how many of them we can fill in the raceway or conduit that we found in Table 4. Table 1 sets the standard. Table 4 gives us the dimensions applied by that standard. And Table 5 gives us the dimensions to fill that standard. Those are your 3 tables for conduit fill. And a lot of this should be review at this point. We've gone over this in class. You've gone over this last year. Make sure you got this in your notes. Those are the 3 tables for conduit fill. Box fill. Box fill, conduit bodies and fittings. Number of conductors permitted in a box. Your box fill code references are found in 314.16. 314.16 gives us what we need to know for sizing box fill. Conductor fill, 314.16b1. Clamp fill, if I have an internal clamp, 314.16b2. Support fill, if I have a lighting support coming out of the box, like a fixture stud or a hickey, the permissions given there to count those as fill in the box is found in 314.16b3. Device or equipment fill, found in 314.16b4. Equipment grounding conductor fill, 314.16b5. So let's break that down a little bit. Conductor fill, that's talking about current carrying conductors, not necessarily your ground. That would just it does count your neutral if it's a current carrying conductor. So we're looking at conductors in the raceway that are actively carrying current. We count each one as one if it comes from the outside of the box and terminates in the box. If it comes through the box, does not terminate, does not loop, it's counted as one. If it comes into the box and leaves the box and it creates a loop without terminating, it's counted as two. If it comes into the box and terminates under a wire nut with another wire and continues on, every wire that enters the box and terminates is counted as one. So if I'm passing it through, I cut it, put it under a wire nut, it's all of a sudden become two in the box when it comes to my counting how many wires are in the box. Clamp fill. If I have an internal clamp, it's going to be counted as one of the largest conductor in the box. So if my largest conductor is a 10 wire and I have an internal clamp, I just added another 10 wire to my count. Same with support or fitting fill. I added another of the largest conductor. Device or equipment fill. If my device is taking up a yoke, which means it's got the two mounting holes that holds the device or the outlet to the receptacle to the box, it's counted as two counts of the wire connected to it. So if I've got 12 wire run into a single receptacle, that single receptacle counts as two more 12 wires. So it would be four total. The two 12 wires that I ran into the box to terminate on the receptacle, and then the receptacle itself. And then equipment grounding conductor fill, 314.16b5. I'm counting the largest grounded conductor or grounding conductor in the box once. Now that's if I have 4 or less equipment grounding conductors in the box. So I'm only counting one conductor, and it's the largest one in the whole box. So if my largest equipment grounding conductor was a 10 gauge wire, I'm adding just one 10 gauge wire to my count. Now if I have more than 4 in there, then I'm adding a quarter of the largest conductor for every equipment grounding conductor over 4. So let's say I have 5 equipment grounding conductors in one J box. And my largest equipment grounding conductor happened to be a 10 gauge wire. I count it as 1 for the first 4, and then I add a quarter of that same count to that conductor. So my overall equipment grounding conductor fill would be 1 1/4 at 10 gauge wire. Now to figure out what each conductor takes up in space, I go to table 314.16b to calculate the total volume used. So table 314.16b tells me what each conductor takes up space-wise in a box. If it's 14 gauge, it takes up 2 inches cubed. If it's, I believe it's inches cubed. Now you got me second guessing myself. 314 400.16, here it is. Yep, inches cubed. This is what happens when you record a video late at night. So, like I said, 14 gauge takes up 2 inches cubed. 12 gauge takes up 2 1/4 inches cubed. 10 gauge, 2 1/2 inches cubed, and so on and so forth. And then you would use table 314.16a to size the appropriate box for that particular installation. Table 314.16a lists for you all the standard boxes, whether they're a device box, whether they're a 4-square box or a 411 box. And it also gives you the maximum number of conductors arranged by wire size that you can put in each of those boxes if they're all the same size wire. So review your boxes, your box fill, 314.16b. Also, before I get too far past boxes, don't forget to review your calculations and your methods for pull box sizing. If it's a 4 gauge or larger conductor and it's in a pull box, know how to size your minimum sizes. Remember, if it's a straight across, if there's no bend, if it's not a right angle bend or a U bend, if it's straight across, it's 8 inches times the largest conduit, and that's it. So if I have a 4-inch conduit on one side and then a 4-inch conduit on the other side and a 2-inch conduit along with it, but I'm only pulling the 4-inch straight through, that means I'm sizing the length of that span between 4-inch conduit and 4-inch conduit. 4 times 8, 32. I need at least a 32-inch box in length in order to use that correctly. Now, if it's an angle pull and I'm looking for the side, the farthest side from where my conduit's open, then it's going to be 6 times the largest conduit plus the remainder on that side. All this is found in Article 314.28. Article 314.28. Review Article 314.28 for instructions on pull box sizing. Now we're in 210, switches. One of the big things for switches that I'm expecting you to know is the maximum height on a standard accessible switch. To the center grip of the handle, no higher than 6 foot 7 inches. On the center grip of a handle. Now that includes if you're moving a circuit breaker and that circuit breaker is acting as a switch. If it is a circuit breaker that is rated to be as a switch, you're going to mount that no higher than 6 foot 7 inches to the top of that switch of the handle so that anybody can reach it and pull it down and turn off the equipment. Flexible cords. Table 400.4 identifies your flexible cords for you. Table 400.5 A, 1 and 2 give you their ampacities based on those cable types. And then 400.5A3 gives you the adjustment factors if you got more than 3 current carrying conductors in a cable or a cord. So table 400.4 identifies the cable, tells you all the properties. Is it used for hard duty usage? Is it used for light duty usage? Is it rated for 600 volts? Is it rated for 300 volts? Etc., etc. Table 400.5 A1 and 2 gives you those cables ampacities based on the information from 400.4. And then if you got more than 3 current carrying conductors, you can make your adjustment factors very much like we did with our 310.15C1 table for our stranded wire. this table works the same, but for flexible cord and cables. So I'd write these down, pause the video, put these tables in your notes. 212, Introduction to AC Theory. We're going to have some questions about AC theory. Understand the ideas of where electricity comes from the magnetism, the moving of electrons from their fixed position to another. Where we'll get into also is inductance. There will be some RLC circuits in your test. So know the definition of inductance, the property of an electric circuit that opposes any change in a current or an electric current. It's designated by an L. The measurement is a Henry. It's not an ohm. It's a Henry. And remember, we have to convert that Henry to ohms in order to use them. That's why it's going to be important that you have that handout with all the formulas that I gave you. Remember, in a resistive circuit, current change is instantaneous, but in an inductive circuit, the current lags behind the applied voltage. In an inductive circuit, the current lags behind the applied voltage. Capacitor, we've talked about those. They have the ability to store a charge. In a completely capacitive circuit, the current leads. Very much like the inductor lagged, a capacitor leads. They have the capacity to hold a specific quantity of electrons. It stores an electrical charge so that it helps counteract the lagging effect of an inductor. The unit of measurement for capacitance is a farad or farads, and that would be a letter F. Continuing with AC theory. The overall opposition to current flow is known as impedance, and that is designated by the letter Z. Impedance, the overall opposition to current flow, or total opposition to current flow in an AC circuit. And your formulas for figuring out your reactance, converting Henrys to ohms. This would be the formula you would use for converting Henrys to ohms. X of L, which is your symbol for inductive reactance. By the way, that may come up in your test. Formula for inductive reactance is X of L equals 2 times pi times frequency times L, or Henrys, and that would equal, or your inductance, and that would equal that formula there. Again, use that worksheet I gave you. That handout will come in handy. The formula for impedance in an inductive circuit looks just like this. Z equals square root over R squared plus X of L squared. Overall impedance is taking the resistance squared, the inductive reactance squared, adding them together, finding the square root of it. We're using Pythagorean's theorem. A squared plus B squared equals C squared. Your formula for capacitive reactance be X of C equals 1 over 2 times pi times frequency times capacitance. And X of C is your symbol for capacitive reactance. Again, you can always pause this video at any time to write these things down. And the formula for impedance in a capacitive circuit is Z equals R squared plus X of C squared. Very similar to the impedance in an inductive circuit. Z is the square root of resistance squared plus capacitive reactance squared. Again, Pythagorean's theorem right there. A squared plus B squared equals C squared. And then the formula for total impedance in an RLC circuit. Impedance is Z equals Z equals the square root of R squared plus XL minus XC squared. And the formula for a circuit current in a series RLC is I equals E applied. That A right there under the E, that stands for applied. So I equals the voltage applied divided by the impedance. Remember that impedance is the fixed opposition to current flow. very much like a resistance. Just a heads up, there is at least one series RLC formula. I'm sorry, for one RLC series question on your final. So please write these formulas down. And then your formula for total impedance in a parallel circuit, Z over T, or Z total, equals E applied divided by I total. Now, in order to figure out your I total, you have to use that Pythagorean theorem formula again. The I total equals IR squared plus, so that would be the amperage of your resistor squared, plus I of L minus I of C squared. So that would be the square root of I of resistance squared plus I of L minus I of C squared in order to figure out your I total for an RLC circuit. So again, these formulas, you have all these formulas. Make sure you have them with you, ready to use on the exam. 215, we started getting into transformers, single phase, introductions, etc. Know your basic transformer terms and theory. Get your notes out, know what your terms for your transformers are. Electromagnetic induction, primaries, secondaries, all that. Calculations for single phase transformers, know your turn ratios. We'll get into that. Applications for transformers, and then your transformer codes are going to be found in 450. A transformer is a device that transfers electrical energy from one circuit to another without changing the frequency. This is accomplished using the principles of electromagnetic induction. That may be a question on the test. I can't remember, but I remember seeing that somewhere. Usually the energy transfer takes place without a change of voltage from the input to the output. That should say change of power. All right. There are 4 basic parts of a transformer. You have your inputs, your outputs, your windings or coils, and then your core. Let's see if this works here. You have right here, that's your input. That would also be known as your primary winding. Over here you have your output, also known as your secondary winding. And then this would be your iron core, used to channel those magnetic lines of flux from your primary to the secondary without wasting those lines of flux. And as that rotating magnetic field passes from one winding to the other, it excites the electrons and sends current down the secondary conductors. So know your basic transformer parts. Turns ratio. Turns ratio is the same as a numbers ratio or a voltage ratio. Your voltage ratio would be your input divided by your output. If you got 480 volts on the input and 120 volts on the output, then you have a turns ratio of 4 to 1. You've divided by 480 by 120, comes to 4 to 1. Voltage ratio and numbers turns ratio is the same thing. Losses found in transformers. You have copper losses, but you also have eddy current losses. Eddy currents create heat in the core and do not aid in the induction process. They are a waste of electricity or a waste of energy. They are referred to as eddy current losses. It's creating work without any return. Therefore, it reduces the efficiency of a transformer. Dissipation of heat. The 2 types of transformers that we talked about for dissipating heat, well, the 2 main ones were ventilated and non-ventilated or liquid filled. Now, single phase dual voltage transformers, series and parallel coils. We spent quite a bit of time talking about this last week. I would encourage you to look over your notes from last week, go back and watch the video from last week, as well as recognizing the grounding and testing of troubleshooting of transformers. Both of those things will be on your final. Again, for just a brief review, transformer can have 2 primary windings, and it can even have two secondary windings. Whatever that transformer is rated, whether it be 120/240, each winding in that rating, for that, let's say it was the secondary, was rated 120/240, each individual winding, X4 to X3, would be rated up to the lower of the 2 voltages given to us. It would be only rated to handle that smaller voltage. And if we wanted to receive the higher voltage that the transformer was rated for, we would need to we would simply need to just connect it in series versus parallel. In here, and I'll leave this on the screen, and you can take a picture of it, you can write it down, are the 4 different combinations for connecting a dual voltage transformer. You can see the primaries coming from the breaker. It energizes the coils. Each of these coils is rated at 240 volts each. If we've connected it to a 480 volt breaker, each of those coils are going to be connected in series so that they split the difference in the voltage, don't burn each other up. And then if we have a 24 volt coil on the other side, we connect them in series to get a 48 volt load, or if we want a 24 volt load, we connect them in parallel. Each of those 2 coils on the secondary side is going to generate each 24 volts. It's up to us what we do with it, whether we make it additive or we make it constant by how we connect it to our load. Another thing to keep in mind with transformers, lug kits do not normally ship with the transformer. You almost always have to order a lug kit. And then continuity checking. Know your electrical continuities when it comes to transformer windings. Let's take, for example, this little transformer here. Each winding is labeled with a marking, whether it be H1 and H2, H3, H4, X1, X2, X3, X4. Per winding, per coil of wire, each coil or each winding will have 2 leads, the beginning and the end. This winding is electrically continuous from one end to the other. It has very little resistance between it. So if you were to put your meter between H1 and H2 and the transformer was good, you'd read somewhere between 2 and 20 ohms. If it was bad, say it burnt out in the middle, you would read OL or infinity, because there's no continuity at that point. But if it's a good winding, if it's a good coil, you're going to read somewhere between 2 and 20 ohms between 2 ends of a winding. If you were to put your meter on the same end of the winding, you'd probably read something like 0. Now, in conclusion of this video, there may be more on your exam that we've discussed here. So it's up to you to study. It's up to you to put in the effort, to get your notes together, to be ready for this test. You may have to go back and look at other recordings. Again, you'll only be allowed to use your code book, calculator, and your notes, as well as the handouts I've given you. Be sure after this video to go fill out that video quiz, which will be available for you on the CMS. In order for you to receive attendance credit for this class, you need to, like I said at the beginning of the video, you need to sign in on the big blue button, comment that you are here, and take that video quiz, as well as the code quiz for tonight's lesson. The code quiz will be there. I'm going to leave that open throughout the night. That code quiz will be open till midnight of Tuesday. So you have all day, all night to take care of that. If you do not turn it in by midnight Tuesday, it will be counted as 0. And I would really recommend you do this quiz, not just for the grade, but you'll gather some good review for the final off the quiz. Again, if you have any questions, reach out to me through email. I'll get back to you as soon as I can. Have a wonderful rest of your evening, and I will see you in class for your hands-on lab. Talk to you later.